In this bag, I have a number of dice. I won't tell you what shapes they have, or if they all have the same shape. I won't even tell you if they are regular fair dice or some weirdly shaped polyhedra. What I will tell you is how many faces they have, as well as the number of edges and corners, which in mathematics are called vertices. This is enough to determine how many dice are in the bag. How is that possible? Setting up an equation system and solve it algebraically is no help to us, since there are an infinite number of possible shapes. But that is not necessary anyway. We are not interested in how many dice of each type there is, only the total number. We will instead use an approach from graph theory and find a property that is invariant for all of our sought shapes, that is convex polyhedra. We will denote this value as capital N. Let's start from a single point or vertex and define n as the number of vertices in our graph. I'll use p as in points instead of v for vertices here, for reasons that will be clear soon. For a single vertex, n equals 1. Now we add a second vertex and connect it to the previous one with a line that we will call an edge. This would have us increase the value of n to 2. However, we note that as long as we keep our graph connected and only connect our new point to one previous point, every time we add a new point, we also add an edge. If we modify our n, we can keep it invariant. If we use our previous definition but subtract the number of edges, n stays constantly equal to 1. Our next modification to n comes when we start to add edges between already existing points. Now the edge number increments by 1, but the number of vertices stays the same. However, doing this creates a new feature in our graph, an area completely surrounded by edges. We will call this a face. Since adding an edge of this kind also adds a new face, we still can keep our n constant by adding the number of faces to it. So for our connected graph, we always end up with the number 1 by calculating n in this way. This is the so-called Euler's formula, or Euler characteristic for planar graphs. Or at least it is a variant of it, since by convention, the surrounding area is considered an extra face, yielding a constant n equal to 2 instead. But the gist of it is the same. If we extend our treatment to a third dimension, we can do something similar to our second kind of edge from before. We can add a new face between already existing edges. That is, no new edge is added. This bumps up our n to 2, and this new face actually corresponds to the surrounding area in the n equal to 2 case of Euler's formula. But by doing this, we actually create yet another kind of geometric feature, a volume. Every time we create this kind of face, without adding any new edges, we also create a volume. Similarly to what we did before, we can keep n constant by subtracting the number of volumes v. That is why we denoted the number of vertices as p before. This is the final modification to n that we will need for our problem, but the pattern actually continues into higher dimensions. If you continue by adding the number of 4-dimensional hypervolumes, subtract the 5-dimensional counterparts, and so on, alternating between adding and subtracting, you will always end up with n equal to 1 for a connected graph. For our problem with the dice, we can consider them to be a graph as well. However, it will not be a connected graph, since they form separate volumes not connected by any edge. This means that every time we create a new die, n is incremented by 1, since we add first vertex of each solid without adding any new edge. In other words, n will immediately give us the total number of dice. So if I tell you that the dice in our bag have a total number of 44 faces, 78 edges, and 44 corners, we calculate n minus v to be 10. But we know that both n and v tell us the number of dice, so they have to be equal. That is, both n and v are equal to 5. There are 5 dice in the bag. Opening the bag reveals that there are 4 6-sided dice and 1 20-sided die. Exactly 5 dice, just as we calculated.